Aloha and welcome to my talk, Nothing But Net. So my name is Patrick Wardle. I am the founder of the Objective-C Foundation. There I work on our free open source Mac security tools. I also author the Art of Mac Malware books and organize the OBTS, or Objective by the C, conference. Okay, so what will you learn today? What are we going to talk about? What are we going to cover? Well, in a nutshell, I'm going to talk to you about leveraging macOS's network frameworks to heuristically detect malware directly on the host. And we're going to do this in 3 or 4 different steps. We're going to start by looking at some Mac malware and see how it interacts with the network, because if we're going to write security tools to detect malware, we need to have at least a basic understanding of how such malware will actually interact with the network. We're then going to talk about how to take a snapshot or enumerate the network state. For example, open sockets, existing connections. We're going to talk about the APIs, the libraries, the frameworks we can utilize to do this. Third part, we're then going to dive into more comprehensive monitoring. Talk about the techniques we can use to develop monitors that are continually, monitoring the network, allowing us to observe network activities. And then finally, we're going to talk about detection heuristics. This is very important because, as we'll see, the first part of the talk is really about how to observe network events. But this is almost meaningless in a way if we can't then tie that back to a responsible process and identify it as potentially being malicious. Because, of course, a lot of legitimate software is also going to be accessing the network as well. So the idea, and this is not some rocket science, is that we are going to attempt to detect malware generically via the network. And this is based on 2, again, very obvious observations, is that A, or 1, malware utilizes the network. So we can see on the slide in a variety of ways: reverse shells, propagation, command and control server tasking, uploads, downloads, file exfiltration, et cetera, et cetera. And so since malware often does this, if we have the ability to observe network activity, we have now a very powerful detection heuristic to detect even novel or relatively stealthy malware. Now, another point I want to make is differentiating between network-based network monitoring and host-based. So at the top we can see, and I have this cool pointer thing, that, oh, maybe not. Okay, it's off a little. I was so excited to use it. There we go. Network appliances is normally how people do network monitoring. The idea is you plop some hardware onto your network and route all traffic through. Now, this definitely works, but requires additional hardware. That hardware might have security vulnerabilities. And most importantly, it's not going to tell you what the responsible process is, for example, a DNS request that you are observing. So I'm all about host-based network monitoring, and that's going to be the focus of the talk today. Again, there's pros and cons to both, but I think there's a ton of pros for the host-based approach. The 3 main pros are, first and foremost, as I mentioned, the ability to identify the responsible process that is accessing the network. This is essential for malware detection. 2, this monitoring and network capabilities, since it's on the host, is also pre-encryption. So if you're doing full packet capture, you don't have to worry about SSL certificates and breaking all that. You just get the raw data. And then, as I mentioned, step 3, you don't need any additional hardware. So in a way, it's simpler. So why are we talking about host-based network monitoring on macOS specifically? Like, why is this a talk? Well, the main reason is it's really not, unfortunately, as easy as we would wish. So buckle up. It's going to be a little bit of a wild ride, but, makes things interesting. So what are some of the problems that we are going to encounter? And I will caveat, today the situation is much better. But over the last few years, as I've been digging into this and developing a myriad of open source tools leveraging Apple's frameworks, I've run into a ton of problems. So again, part of the talk is to show you some of the pain points, talk about the blood, sweat, and tears, so that if you're developing networking monitoring tools, you will not be, you won't succumb to this. So first and foremost, Apple's networking code, especially in the past, has been buggy. An example, I released Lulu. It's an open source firewall we'll talk about. And it talks to Apple's kernel mode components. Lulu itself is 100% user mode. Unfortunately, I got a lot of bug reports that Lulu was panicking the system. And I was like, that's strange, because again, it's all in user mode. Well, what turned out was that there was a bug in Apple's kernel components that Lulu was inadvertently triggering. But really wasn't my fault. Like, why do I get the bug report? Downsides of doing open source tool development. So pass this on to Apple. Good news, it's now fixed. But this is kind of an example of some of the quality of Apple's networking code. Less than ideal. Other problems with Apple's code, a lot of the frameworks we're going to talk about today are private, means they're not documented, kind of use at your own risk. Even though they're very powerful, Apple has yet to document them. This is very frustrating. It requires us to do some reverse engineering. And then thirdly, documentation is rather lacking. A lot of times you look up an API or some constant, and there'll be like 5 Google results, and most of those are just header files. So again, a lot of kind of blood, sweat, and tears, but hopefully we'll cover all this in the presentation so you don't have to deal with that. Another issue that I ran into was the fact that Apple rather surreptitiously actually subverted a lot of the network capabilities without telling anybody. This was rude. So what happened a few years back is kernel extensions were the predominant way that we wrote networking tools. Firewalls, filter monitors, et cetera, et cetera. Apple said, hey, we're trying to move kernel extensions away. No third-party kernel extensions. So we'll move everything into user mode and give you new user mode frameworks that you can leverage. We're all like, okay, actually this is great. Developing kernel code sucks. If you screw up, you're going to panic the box. Much better to do it in user mode. Well, what Apple didn't tell us is surreptitiously they created an exclusion list where a handful of system processes and daemons were actually exempt from being routed through these user mode network extension frameworks that our network security tools would utilize. So this meant that if you wrote a firewall subscribing to Apple's best practices, there was actually traffic that would skip it, kind of by design. But again, Apple didn't tell anybody. Obviously, this is a huge problem from a security point of view. It took me like 2 minutes to find a way to abuse one of these legitimate exempted processes to generate network activity, network traffic on my behalf to talk to my own command and control server. And again, since these processes were exempt from being filtered through any of security tools, we were essentially blind. So it made a ruckus. Apple got some bad press, which for better or worse, is the way we get Apple to change their course. And Apple now has removed this exception list. But again, this is kind of showing you where there's some road bumps along the road. Okay, with that overview out of the way, let's now dive into talking about some Mac malware specimens that use the network. Again, we need to do this so we can kind of get a sense of what we're looking to detect in the first place and what kind of network activity we might see. So first off, we have dummy. I named this malware sample dummy because it's very simple and straightforward. That having been said, it's still sufficient to allow an attacker to completely control a remote system. So what dummy does is it persists a bash script. And if we look closely at the bash script, we can see it's just executing some Python code, some Python commands that do 3 things. First and foremost, it's going to directly connect to a remote command and control server. It's then going to redirect standard in, out, and error to the socket that just was created, and then spawn an interactive shell and tie that to the socket. This is a vanilla reverse shell that allows the attacker now to execute commands on his or her remote system that will be executed on the infected system. So again, dummy reverse shell. Another interesting piece of malware is IP Storm. This is interesting for a variety of reasons. One of those reasons was it was originally developed for Linux and then was ported to macOS. So this is a trend we're seeing where adversaries are realizing there are a ton of Mac systems, especially in the enterprise, that are very juicy targets. So the IP Storm malware authors ported it to Mac and deployed it. Now, IP Storm, from the networking point of view, does 2 interesting things. First, it tries to propagate itself by brute forcing into other systems via an SSH attack, basically password guessing. So it almost has some worm-like capabilities, which again, this is an interesting heuristic that perhaps we can observe on the network. Once it's successfully accessed, hacked in, gained access to a remote system and infected it, it also sets up a reverse shell or a remote shell. So again, this is something that if we're monitoring network activity on the host, we should be able to observe. Thirdly, we have GoRat. GoRat is a fairly standard but feature-complete backdoor for macOS. On the slides, we have some of its capabilities, things like upload, download files, pretty standard for a backdoor, but again, will generate some network activity that we can observe. It also, though, has other capabilities that we don't see that common in Mac malware that allow it to interact with other systems over the network. For example, it has the ability to do a port scan. So again, generating more network traffic. It also has the ability to set up a tunnel and a proxy. So again, networking opportunities. One interesting thing also about GoRat is it takes all its network streams, its multiple streams to the command and control server, and bundles them all into one single connection. So it actually multiplexes its connection. So again, kind of interesting from a networking point of view. We also have supply chain attacks that via network analysis might be the best way to actually detect these. And we'll talk a little bit more about the 3CX one. But this was interesting because it targeted a lot of Mac systems, unfortunately very successfully. And the reason is the North Korean hackers were able to infect the build server and then surreptitiously inject malicious code into 3CX's desktop application. They then submitted this application to Apple. Apple naively and inadvertently notarized it, which basically meant this application was now approved to run on all versions of macOS. Users, really to no fault of their own, downloaded and ran this, saw it was signed and notarized by Apple, inadvertently infecting themselves. Now, how was this detected? Well, if we pop on the forums, we can see that one of the victims basically said, hey, I observed some strange DNS traffic, or my EDR observed some strange network traffic that I was able to track back to the 3CX application, and this is how I was able to uncover the attack. So again, very powerful, right? Normally, 3CX's application should only be talking to 3CX's server. If it starts talking to some like random Russian IP, like that's a great way to perhaps figure out something is amiss. Finally, briefly want to mention iOS malware. This talk is predominantly about macOS, but a lot of the network capabilities and frameworks we use are also available for iOS, but I haven't dug into that. iOS, more than any other malware, in my opinion, is incredibly difficult to detect because iOS is essentially a black box. You cannot even run a process listing on a non-jailbroken iOS device. So once malware gets into that, and we all know nation states have 0 days to do that, remotely infect iOS devices, they are going to sit in there happy and undetected. A great recent example is the triangulation attack that hit Kaspersky. For over 4 years, Kaspersky's phones, so phones of their employees, were infected with a very stealthy malware. So this again just drives home the fact that even Kaspersky, one of the world's best malware detection companies, was unable to detect this until they noticed some anomalous network traffic, then uncovered the infection. So again, if you're doing iOS analysis and detection of malware, network monitoring is the best. And you can do some host-based network monitoring on iOS. So hopefully I've driven home the fact that host-based network monitoring is a good idea, and there's a lot of malware now targeting Macs that has a network footprint that we might be able to detect to generically uncover all these infections. So now let's talk about how do we observe network activity in the first place, starting with file descriptors. So the idea is pretty straightforward. You can do it in about 3 steps. And the idea is on macOS, which is kind of BSD-like, Unixy, sockets are also file descriptors. So this means if we can find a way for the operating system to give us a list of all the file descriptors opened by a process, any sockets, listening sockets, network connections, et cetera, will be in that list that then we can query. So 3 steps, and we'll go through each of these in detail in code. Now, I do want to point out the code on the slide is maybe more for a reference. So if you're going to be coding up some network tools, grab the slides afterwards. I didn't want to be up here for 45 minutes walking through code. So I'm going to jam through some of the code samples pretty quick. But again, I want to give you the idea of how you can approach this. So in a nutshell, our goal is, again, to receive a list of the file extensions. So what we're going to do is we're going to invoke the proc_PID_info API. We give it a PID of the process whose file descriptors we want. We first execute it with nulls, so it gives us the size of the buffer we need for those file descriptors. After we allocate that buffer, we then execute it again to get the actual list of file descriptors. And again, this is going to include file descriptors for open files, but also sockets. So now what we want to do is iterate through that list, throwing out any files and honing in just on sockets. So again, code on the slides. We basically iterate through that. And for any file descriptors that are sockets, we can invoke the proc_pid_fd_info API that says, please give us more information about this specific file descriptor, which is a socket. Next up, we're getting closer. We want to filter out everything but network sockets. On macOS, you have things like Unix sockets, which are local IPC mechanisms. Here, we don't care about them. So what we do is we check out the family of the socket. And if it's not an AF INET or AF INET 6, so IPv4 or IPv6 socket, we ignore that. So now if we take this code and compile it and run it, we run it against something like GitHub Desktop, we can see that this application has about 70 file extensions open, file descriptors, and only a few of those are sockets. Now, we haven't extracted any specific information yet from those sockets, but we've whittled down our list. I'm using GitHub Desktop as an example, and we'll use it in several slides as well for two reasons. One, it has a bunch of network connections. It's running on my system, so it's easy to test. But also drives home the fact that, obviously, legitimate software is also going to access the network. So when we get to the end of the talk, again, we're going to focus on how to differentiate between good and suspicious or unauthorized network activity. But again, in order to do that, we first have to figure out how to get information about that. So now we have networking sockets. Let's figure out how to get more information from them and extract that. So for UDP sockets, it's pretty easy. We have the protocol, and then we can get a local port. But because they are stateless, UDP, stateless protocol, we can't get much more information about that. TCP sockets, though, there is a myriad of information. Again, I'm not going to jam through all the code, but you can see we can pull out, obviously, local information, but also the remote endport and port. Having this information is really great in perhaps detecting connections to unauthorized command and control servers, et cetera, et cetera. If we compile and execute this, no surprise, we get a list now of GitHub Desktop's network connections with all the information we want, remote destination, family, state, et cetera, et cetera. Awesome. We run this against dummy. As expected, once it's connected out to the attacker's command and control server, if we enumerate the file descriptors for the Python instance that's running the back door, we see the connection. Now, you might be wondering, OK, great. I see that Python is connecting out to some server. Like, how do I know that's malicious? Hold that question. We will answer it. It's an excellent question. Now, I want to talk about enumerating network state using the private network statistic framework. And why do I want to talk about this? Well, the approach we just talked about using the proc_pid APIs is solid, but it has a few limitations, or rather maybe cons. So first and foremost, it's process specific. So you only get the file descriptors for a specific process. Yes, you could iterate over all processes and get a list for all, but that's extra code. Also, then it gives you all the file descriptors. You have to whittle down the list to just the sockets. And finally, you also don't get any network statistics. Like, I want to know how many bytes are being sent up or downloaded for a specific connection. Well, turns out macOS has a tool that does this. So if you're on a Mac system and you run nettop, it will give you a global list of all the network activity, a snapshot of who is talking to whom on your system. This is global. It's only sockets and network connections. And it also provides statistics, bytes up and down, which is very useful for malware detection. So unfortunately, nettop is closed source, which means we have to do some reverse engineering. If we look at its dependencies via the OTool utility, we can see that it is linked against a private framework called network statistics. The well-known security researcher Jonathan Levin actually reverse engineered this framework and wrote an open source tool called NetBottom, which is, well, essentially a command line based open source implementation of nettop. So kudos to him. A lot of credit there. So based on Jonathan's work and some further reverse engineering, I built a tool called Dedicate, which is a UI tool that utilizes the private network statistics framework to give you all the information about network activity on your system. So it organizes this by process, which is helpful. We can see it identifies the protocol, the interface, the state of the socket, but also statistics about the bytes going up and down. As I mentioned, this is useful, for example, perhaps to detect if malware is exfiltrating a large amount of data out of your network. This tool, like all of Objective-C's tools, are free and open source. So if you want to dive into the code a little more, check it out. However, we will dive into the core of the code here because it's actually pretty simple. Again, leveraging APIs from the private network statistics framework. So how do we get this global list of network activity using this framework? Pretty easy. We first create an nstat manager. Once we've created that manager, we set a callback block that will be invoked in a second. Then we tell the framework what type of connections and activity we're interested in. So here we say both UDP and all TCP. We want everything. And then what we do is we start a query. What this will do is trigger a call into the framework, which will then tell the operating system to enumerate all of the network activity. And for each connection, for each source, that's kind of Apple's parlance essentially for a socket event or a networking connection, it will call our callback block with a ton of information about the socket. If we then link in the network statistics framework and compile it, we can see when we execute this, it gives us a ton of information. A little hard to see, that's almost by design. I really just want to show you how much information that this private framework will give you for each and every network connection, open socket, et cetera, et cetera. So this is just from one connection from GitHub network. GitHub desktop, sorry. And we can see, yes, it has the responsible process, but also transmitted bytes and a ton of other information. So super useful. Now, the main problem, I always like to talk about pros and cons between the two approaches we've talked about so far, is that they are essentially snapshots of the network state. Yes, you can re-execute them to kind of get snapshots over time, but an obvious problem is if malware is not actively utilizing the network when you perform your code executes to grab the snapshot, it's not going to show up. So for example, dummy, we can see sleeps every 5 seconds if it can't connect. So if you run your snapshot while it's sleeping, you're not going to see dummy's connection. The 3CX payload, as we can see the quote on the slide says, it sleeps also before connecting out. You can imagine other scenarios where malware beacons perhaps once an hour. If your snapshot is somewhere between its beacon interval, you're going to miss it. So what we now want to do is talk about more comprehensive approaches that provide continual monitoring of the network. And we're going to start by building a DNS monitor. The idea is that I think we should be able to efficiently detect malware by monitoring its DNS resolutions. Again, this is not a brand new idea, but a powerful one that I want to show you how we can do that directly on the host. So back to the 3CX supply chain attack. Again, this was essentially detected by its network activity. So again, check for network-based detections. We can see that, obviously, you all know how DNS works, but when the malware gets on the system, it's going to attempt to resolve the domain name of the attacker's command and control server. As I mentioned, normally 3CX should only be talking to 3CX servers, but via the network, perhaps we can see it trying to resolve a brand new suspicious domain. So the idea is, hey, can we just monitor DNS requests, tie those back to processes, and then detect if that's unauthorized or potentially suspicious? So if you're going to be doing network monitoring on macOS, you're going to be using the network extension framework. This is a very powerful framework, allows you to create user mode network monitoring tools. And Apple, unlike some of its other frameworks, actually documents it reasonably well. You can do a host of really impressive things with the network extension framework. Some of these are listed on the slide. We're going to focus on the bottom two, which is developing a content filter for all traffic. We'll talk about that next. And now what we're talking about, how to monitor for DNS traffic. There's also a great WWDC video. Have a watch. It explains in detail exactly how to utilize that. So to create a DNS monitor, what we're going to do is we're going to create a DNS proxy. And the idea is that all requests from any application, process, daemon on the system is going to be proxied through our network extension, which is also running on the host. So we'll be able to see that. We're then going to proxy that request out, get the response to also see the answer to that request. So I was like, great. I saw this in Apple's documentation. Looked like it did exactly what I needed. Googled it. First hit is Apple's documentation. Second hit is someone being like, hey, this looks awesome. How do we do this? Which was exactly my idea. So I was like, yeah, well, no one really knows. There's not a great example. Like, this is obviously doable because Apple has documentation, but they don't provide example code. So I wanted to build an open source DNS monitor as a learning experience, but also to illustrate how one would do this. For example, if you want to build this into your own security products. So the tool is very creatively named DNS Monitor, and it's a host-based DNS monitor, and also, as we'll see, blocker for macOS. It's available on Objective-C's website and on GitHub. And you can see when we execute it, it does two things. First, it identifies the responsible process. Here we're just doing a NS lookup for Objective-C. And then also the DNS packet, in this case the query for the domain we need to resolve. Perfect. This is all the information we want. So how do we do this? Well, before we can dive into some code, we have to talk about some prerequisites, because unfortunately there's a lot. Apple somewhat understandably says network extensions are very powerful. You can see network traffic, so we're going to leverage a bunch of requirements upon you. So if you're going to build your own, you first need to obtain an entitlement for Apple, which may require some begging, some sacrifices to Cupertino, get on your knees. Eventually, they'll generally acquiesce and give you the necessary entitlement. Now, when you're building your DNS monitor or network extension, this will also be true for our content filter, which we'll talk about next, you have to bundle it up into an application bundle, specifically in the contents library system extension folder. So your application needs to have a certain structure. And we'll show why and a reason. Then you also obviously have to sign and notarize it, which is pretty standard. So, I mean, this is kind of a pain, but way less painful than this. So you've developed a network monitor. You want your users to install it. Play around. OK, what do they have to do? They have to click Allow to download it. They then have to click Open to open it, even though it's signed, notarized, and entitled. They then have to click Open System Preferences, go into System Preferences to approve it, which requires them to put in their password. And then once it begins capturing network traffic, they have to click Allow to that as well. So that's 1, 2, 3, 4, 5, 6 different amounts of user interaction. Again, for an application that is entitled, meaning Apple gave you explicit approval, it's signed and notarized. So this kind of bugs me, and I don't know if you all remember, I might be a little older than some of you, back in the day, Apple made this really snarky commercial ragging on Windows Vista, because Windows Vista apparently prompted you a lot. And well, you might not remember it, so I wanted to show you the video, because I think it's hilarious. So again, this is an Apple commercial making fun of Vista, and we'll draw our own conclusions, but it's also a nice break for me talking.
Mac has issued a salutation, cancel or allow.
Allow.
So one allow.
You're returning Mac salutation, cancel or allow.
Allow.
Okay,
Two.
Mac is asking a question, cancel or allow.
Allow. He's part of Vista, my new operating system. PCs have a lot of security problems, so he asked me to authorize pretty much anything I do.
You're pointing out Vista's flaws, cancel or allow.
Allow. I could turn him
Four.
off, but then he wouldn't give me any warnings at all, and that would defeat the purpose. So.
You are coming to a sad realization, cancel or allow.
Allow.
5. So how many prompts did Mac take to install the network extension? It was 6. So to me, it's kind of hilarious that Apple is like ragging on Windows and now has like fallen to that level. So kind of annoying, kind of hilarious. Ugh, is what it is. So we're not here to brag on Apple too much, but I did think that was a valid point to make. So now let's dive into how we would actually go about creating a network extension, which is a type of extension called a system extension. So first, we're going to talk about how to install or activate a system extension. Again, I'm not going to go through all the code. I'm going to talk about some of the concepts. So 3 things. You're going to create a request to activate the system extension. You're then going to specify the class that implements various delegates that will be called as part of the system extension activation process. And then you will submit the request that will actually trigger the system extension. Now, in that system extension, we want to utilize network extension logic here, monitoring DNS traffic. So what we have to do is tell the system that that's what we want to do by implementing a class that inherits from the NE DNS proxy manager class. This is a little more involved, 5 steps. We load the current preferences for this. There might be other filters, proxies installed in the stack, so we kind of load that first. We then set some descriptions, initialize and configure it, tell it what type of network extension we are. Again, this NE DNS proxy manager. We set the enable flag, and then we save the preferences, which will trigger the network extension to be loaded and activated. You can use the system extension control utility that ships with macOS to view loaded extensions. And here we can see now our network extension, which is going to proxy DNS traffic, is up and loaded. Behind the scenes, Apple has copied this out of your application bundle into the library system extensions folder and loaded it from there. Now, our network extension is up and running, but we actually haven't done anything yet. So the first thing we need to do is call the Start System Extension Mode API. Apple says in your network extension, call this right away. Behind the scenes, macOS will consult the info.plist file, which should specify what class in your network extension is going to implement the actual network monitoring logic. So for example, in this case, our NDNS proxy provider. So you can see on our slide, we've created a class that inherits from that. Now, this class should implement various required delegate methods. These will be automatically called by macOS. Start and stop are pretty self-explanatory. They simply allow you to do some initializations and cleanup. The handle new flow, though, as we can see on the slide, will be automatically invoked by the operating system anytime a network event occurs. In this case, since we're monitoring DNS traffic, anytime a DNS request occurs. So this is great. Now we can handle that. Now we have to remember the class is called, DNS proxy, which means we're essentially now proxying DNS traffic, which means we have to take some responsibility for handling the flow. So what we have to do is 6 steps. We'll talk about the first 4 here. When a DNS request is generated by any application program on the system, this is going to invoke our handle with new flow method. What we then do is open that flow, read the datagrams locally. We then connect out to the DNS server and write the datagrams to proxy it on. So this is how we proxy the request out to the DNS server. Obviously, in the middle, we can examine, log, block the request. We'll get to that in a second. On the flip side, we are also responsible for handling the DNS response. So we have to read from that remote endpoint and then write that back to the local flow, which completes the DNS resolution process. And the local application is none the wiser and has gotten a response to their DNS request. Now you might be wondering, rightfully so, how do we parse these DNS packets? I initially thought I was going to have to do this myself. Bad idea. Turns out there's a somewhat unknown, relatively unknown libresolve library that does this for us. So on the bottom of the slide, you can see if we give the DNS parse packet function a raw DNS packet, it will parse that packet into a nice structure for us. We can then simply print that out or reach in and now pull out individual pieces from that lovely parsed DNS packet. This is great. You don't have to do any DNS parsing yourself. Now, what we haven't talked about is how to identify the responsible process. I've said multiple times this is the main benefit of host-based network monitoring. So let's talk about how to do that in the context of a network extension. Turns out it's pretty easy because the flow that is delivered to us for any network activity contains an audit token. If you're not familiar with audit tokens, they're essentially a secure, modern way to uniquely identify a process. They're more like secure than PIDs, which could be potentially reused. So once we have an audit token, which every flow has, from that we can extract a PID, a path, all the information needed to identify the process responsible for, in this case, the actual DNS request. So here's the output from this tool. If we compile it all and execute it, we can see 2 main things. At the top, we can see that it has identified the responsible process, the 3CX desktop application. And then we also now intercepted the query specifically to the msstoragebox.com. So hooray, we're now intercepting DNS requests. Well, we might want to block requests. So how do we do that? Well, we can either block the question, the query, the request, or the response, the IP address when it comes back. So let's first talk about how to block the initial query, the question. As we can see on the slide, when we get the request before it's gone out, we can parse it to see what the question is. What domain is the application trying to resolve? And if it's a domain we don't like, for example, it's in a block list, we can just close the flow. If we do this, for example, here I've told it to block google.com in a block list. I then try to resolve google.com. We intercept that request and say, no, we don't want you. And the request just times out. So we have the ability now to block questions. Of course, we can also block the answer because the answers come back to us via our proxy. The answers are obviously going to be IP addresses. So if you have a list of IP addresses you want to block, essentially same thing when that request comes back, you just close the flow without writing to the local flow. And again, this will cause the DNS request to simply time out. You could also do other things like write, or send a custom packet saying, IP address not found, reroute it, whatever you want. It's a proxy. Another neat feature of this tool is the ability to dump the DNS cache. This is actually one of the main reasons I wanted to write this tool in the first place. I just wanted macOS to tell me what IP addresses had been resolved from what domains. So you can send it a signal, and it'll just dump to you all the requests and the IP addresses. Now, there's one obvious shortcoming, and that is if malware connects directly to a command and control server via an IP address, this is not obviously going to generate any network traffic. So in the case of dummy, we run into this instance. It connects to a hard-coded IP address, no network traffic. Our DNS monitor is not going to see anything because there's no DNS traffic. So now what we have to do, if we want, is to create a more comprehensive tool that can see all network traffic and also block or deny based on rules. So I briefly want to end by talking about Lulu, which is an open source firewall I wrote for macOS. Again, source code on the Objective-C website. And while we all know what firewalls do, they basically observe traffic. If it's from a trusted application, it allows it through. If it's from something it doesn't recognize or something the user has said we should block, we throw up a prompt or simply block it. So the way you implement this is very similar to the DNS monitor. Again, we're going to use a network extension, but in this case, instead of using the DNS proxy class, we're going to use the NE-filter data provider class. And as we can see on the slide, Apple documents and says that this will allow you to see all network traffic and then also allow you to make decisions based on this. Now, we'll talk briefly at the end how to classify the traffic to tell the system whether it should be allowed or denied. But this basically comes down to examining the responsible process and also preferences or characteristics, rather, of the traffic. Or we could ask the user. So how do we enable the filter manager? Exactly the same way as the DNS proxy provider. It's also a network extension. Although there's a few things that are different. For example, we can customize it a little more to tell the operating system what type of network traffic we want. Specifically, do we want packets or not? We don't want to do a full packet capture, so we set no, but we want to filter, monitor all sockets, so we say yes to that. We then save those preferences. Again, this activates the filter. We're off and running. Again, we have this handle new flow. This is the same delegate method that gets called, but in this case, it is expected to return a verdict to the operating system that tells the operating system either to allow, block, or pause the flow. Now, if you want to just passively monitor all network traffic, you could just hard code your application, your network extension to always return allow. All right, so let's end by talking about how do we now determine if network traffic is malicious. Up to this point, we've talked about several ways that allowed us to collect this network activity or monitor network connectivity. But at the end of the day, we want to be able to classify this as legitimate or unauthorized, suspicious, potentially malicious. So there's two main ways to do this. One way is via the responsible process, which we'll talk about next. The other way is by examining the characteristics of the actual network connection. This is a well-known topic, a well-discussed topic. There's books on this. There's talks about this. Basically, now we have access to the network connection. We can come to conclusions. For example, if there is a listening socket that's bound to an external interface, might want to take a look, especially if it's listening on some strange port. If there is a connection that statistically is weird in the sense that it beacons every hour and exfiltrates a large amount of traffic at midnight every night, you might want to take a look. However, what we want to dive into is, because we're running on the host, how to check the responsible process. Because that example I just gave, something beaconing at midnight and sending a large amount of data, that could just be your enterprise backup solution that's like backing up every night at midnight. If you're executing in a network application, you might not be able to identify that it's the backup solution. But since we're on the host, we can see the responsible process. So how do we identify the responsible process? We already talked about that. How do we classify or examine it? What characteristics make it potentially suspicious? Well, there's a whole different ways you can do that. We're briefly going to talk about some ideas that I like. We're going to start by talking about how to determine if an item is not notarized and doesn't belong to the operating system. The idea is most malware is not notarized. There's some exemptions. The 3CX payload is one example. But the vast majority of Mac malware is not going to be notarized. So if you see network connection from a non-notarized process, that's a red-ish flag, especially because the vast majority of legitimate software is going to be notarized. So pretty easy. Once we have a PID or an audit token from a responsible process, we can create various requirement queries against it. I have some example code from here on the slide. We basically can say, does it belong to Apple? Is it notarized? And the operating system will say yes, no, maybe, et cetera, et cetera. I've implemented this in another one of my tools called BlockBlock. It's not related to network activity, but does have the full code how to classify a process if it's notarized or not. We also might want to say, is it persistently installed? On recent versions of macOS, you can answer this question by looking at the background task management or BTM database. This is undocumented, but I've released an open source tool that can dump this database. Here we have the persistence information about dummy. We can see that dummy persists as a launched daemon, as a script that executes as root that's not signed. These are all very suspicious things. And speaking of dummy, remember it ultimately executes Python to connect out to spawn a reverse shell. And the question was, how do we know this instance of Python is suspicious or not? One great answer is to look at its process hierarchy. So once we have the network connection that we want to examine, we have an audit token or a PID from that, we can look at the process hierarchy. In this case, we can see that that Python instance was executed by bash, which was executed by launch D. We also, as we showed on the last slide, have persistence information. So now what we have is an instance of Python that's running as root, that's persistently installed, that has an established connection to an unknown IP address. Those are all red flags. And even though Python is being used, and Python itself is not malicious, it's been used in a very suspicious way. And in that case, you probably would want to go, you should go, take a look at that closer. All right, let's wrap this up with some takeaways. Okay, again, obviously malware uses the network. I've hopefully made the compelling case that we can detect malware pretty consistently and reliably by detecting unauthorized traffic directly on the host, leveraging Apple's networking frameworks. Now, if you're interested in learning more about malware analysis, I've written a book on this topic. It's 100% free online, so you can pop over to taomm.org and grab that. I'm also excited to announce that I'm working on another volume which talks about this exact topic, which is programmatically detecting Mac malware in the first place. So check that out if you're interested in malware analysis, malware detection on macOS. Also more, if you enjoy my talks and my ramblings and poking at Apple, I'm going to be doing a tool arsenal tomorrow at 10 a.m. where I'm going to be demonstrating the tools I've talked about today. So stop by. We can talk about the source code. You can see this in action against some of the malware specimens I talked about. I'm also going to be doing a book signing with Maria, who gave the keynote, and that will be tomorrow at 12:15. So if you want to pick up the book, which is awesome, get it signed. Maria's book is essential as well. It's on ARM reversing, which on macOS is now what all binaries are essentially written in. Check that out. And then finally, tomorrow as well, I'm going to be talking about the 3CX supply chain attack, which we touched on today. The talk tomorrow is going to be diving into analyzing the macOS payloads. So a lot of interesting reverse engineering, talking about supply chain, kind of neat stuff. Lastly, I briefly just want to talk about the Objective-C Foundation, who I founded and support, because I think we're doing a really neat job with some community-focused efforts that I would love for y'all to learn more about and perhaps become more involved in. So we're a full 501c3 nonprofit. We organize the OBTS Mac Security Conference. We provide college scholarships to college-bound students focusing in tech careers. And we also have a bunch of diversity programs where we're trying to, well, make tech a little more diverse. So pop over to objectivec.org, learn about us, maybe support us. And speaking of, I want to end by thanking the amazing companies who support the Objective-C Foundation. Without them, I wouldn't be up here today. The OBTS conference would not be a reality, the books, the free tools, so big thanks to all of them. So that is a wrap. I went over by a few minutes, but since this is the last talk of the day, we can still take some questions. I will also hang out here for a few minutes. So if you don't want to raise your hand, you can also come up and chat with me. But thank you again so much for attending this talk. I really appreciate your time and attention. Mahalo. Any questions? And if so, use the mic so the live stream or recording can pick that up. Yes. Just walk up and ask away. And make sure it's not too hard.
Yeah, I was just wondering, do we have anything that we can use to monitor, say, encrypted DNS going out of the system? Usually it looks like it's on port 443. It looks just like any other TLS traffic. Great question. So the question was, how do we monitor encrypted DNS traffic? Wow, that's a great question. I'll have to get back to you. I don't know off the top of my head. It would be interesting to see if that would be routed through the DNS proxy provider, because according to Apple, all DNS traffic would go through that. Yes, and I put that in quotes. Apple is semi-receptive if you provide them feedback, like, hey, it'd be great if encrypted DNS traffic is also routed through the DNS proxy. Otherwise, adversaries or whomever is using encrypted DNS, we would miss. I don't know the answer to that. It'd be a great thing to test. If you run the DNS monitor and then make an encrypted DNS query, if it shows up, it means awesome. If not, probably means currently we're a little bit out of luck. However, the network filter extension that Lulu is built on top, that sees all network traffic, so you might capture it there. And in theory, I think that would be before it's encrypted. Again, something to look into, but excellent question. Other questions? I don't think so. I can repeat your question, so yeah.
If you're connecting directly without using the system processes to like port 53 of a DNS server, does that go through macOS's services that you're using?
Excellent question. So the question is, if you're, and tell me if I'm getting wrong, directly connecting to the DNS request, doing it yourself, does that still get routed? This is another question I do not have the answer for, which is great because I think this illustrates that this is a great topic, that there's still a lot of unknowns. Like even myself, who has been doing this for several years, I don't have all the answers. And so that would be something great to test. If malware makes its own DNS request, is this going to get routed through? I would hope so. I'm wondering if Apple basically just takes port 53 traffic and then proxies it through, because when you intercept a DNS request, they give you the responsible process. It doesn't come from like their MDNS responder, which is kind of how system requests are resolved. So I could see potentially. It would be interesting, though. Again, something we should be able to test. Run the DNS monitor, make your own DNS requests via raw TCP sockets to a port 53 and see if that gets routed through. If not, that would be, again, something worth noting and a limitation of the DNS proxy, which, again, is maybe a check mark for the more comprehensive network filter driver extension, which, in theory, should see all network traffic. And at that point, you can see, oh, hey, this is a raw DNS request, which might be suspicious unto itself. So great question. Any more? Awesome. Thank you again so much. It was a pleasure.